chapter 15 is going to be all about integrating these real valued functions of more than one variable. So in 15.1, we're starting with double integrals over rectangles. Okay. So at the top of the board here, I've reminded us what we mean by a single integral. So if f of x is a real valued function of one variable, the integral from a to b of f of x dx represents a signed area. So that's the signed area between the graph of f of x and the x-axis over this interval from a to b. We think of f of x as being like our height function, and the rule is when the height is positive, so that the area lies above the x-axis, we count it as positive. When the height is negative, so that the area lies below the x-axis, we count that as negative signed area. And of course, signed area is often just a metaphor for some other signed quantity that we might be calculating, like displacement or work or something like that. Okay. All right, now what we're looking at in this section is going to be something that looks like this. The double integral, which I write with two integral signs, over r. R is just going to be some region in the xy plane. Okay. Now, for this particular section, we're restricting ourselves to looking at rectangles. But R does not stand for rectangle, R stands for region. Because as we move on, we're going to retain this notation, but allow R to be a blobular region. I think blobular is a very important word. It means blob-like. Okay. So, essentially, we're going to be thinking of f of xy, which gives us a z-value, as a height function. So, to all points in this region in the xy plane, we're assigning a height. And that height could be a positive height or a negative height. Now, I've drawn a picture here, and just for the sake of keeping my picture simple, I chose to draw a function that was always positive over my region R. Okay, but we're going to use the same rule. When the height function is positive, so that our volume lies above the xy plane, we will count that as positive signed volume. When our height function is negative, so that our three-dimensional region that's contained between the xy plane and that surface is below the xy plane, we will count that as negative signed volume. Okay, and you'll notice we write this dA. That A, you might guess, stands for area, because we're essentially thinking of area of the base times a height. Okay. Now, I know that when we calculate a single integral, we do it by going through this four-step process. And we've talked about that before, but I'm just going to review it real quick here, and then we're going to generalize it here. Okay. So the first thing we do is we chop. We take the interval from A to B and we chop it up into little pieces. And there's no requirement that we chop it up into pieces that are the same length, but it's usually simpler if we do. And of course, chopping up that interval induces a chopping of this region into little strips of area. And so then we approximate the signed area of each of those strips. And we do that by saying, this piece right here has kind of a funny shape. I don't have a geometric formula for calculating the area of that shape. It's rather inconvenient that the height is changing like this. So we employ the very powerful mathematical tool of denial. We choose a representative x value, we pick the height at that point, and we pretend the height doesn't change. We treat it as if the height is constant over that interval. And we do that for each one of these subintervals. And so we create a bunch of rectangles. And we calculate the signed area of those rectangles, and we add them up, and we call that a Riemann sum. So that would be the sum, as my index I goes from 1 to n, where n would just be the number of rectangles that we've chopped things into, of f of xi star, where xi star is just the representative x value I chose for the ith subinterval. X because it's an x value, I because it's in the ith subinterval, and the star there is just because, generally speaking, we would have already used the symbol xi. When I partition the interval AB into little pieces, I usually would call the endpoints x0, x1, x2, so that xi would actually be the right endpoint of the ith subinterval, and I'm not required to choose the right endpoint. Okay. So we take that, and then we multiply it by delta x, so that we've got a base times a height, and then this represents the area of a rectangle. Then, of course, what we do is we take the limit. Now, if we've used a regular partition so that the bases are all the same, it's sufficient to just let n go to infinity. That will force the bases to shrink to 0. If I used an irregular partition, I need to make sure that I take the limit in such a way that all of the bases shrink to 0. Okay, so what we're going to do is we're going to generalize that 4-step process, chop, approximate, add, take a limit, and see if we can come up with a definition for our double integral. So step 1 is to chop. Now I'm going to just draw a picture of my region in the xy plane here. The region that I've drawn for this example happens to lie in the first quadrant with the axes as 2 of the boundaries. That doesn't need to be the case. So I don't need to be going from 0 to somewhere, but I'm going to draw it so that it matches with this particular picture. Okay. Now, what I'm going to do is I'm going to chop things essentially twice. I'm going to first chop up the x-axis into little pieces, like so, and then I'm going to chop the y-axis into little pieces as well. That's it. Get a better marker. There we go. Okay, so what that does is if I extend these marks, chopping x divides this rectangle into these vertical strips. Chopping y gives me these horizontal strips, and I've essentially chopped things up into a bunch of little subrectangles. Now the notation I'm going to use, I was chopping twice. I was chopping the x interval and the y interval. So I'm going to have an index for each of them. Okay? And then the number of subintervals doesn't necessarily have to be the same. So I'm going to use an index of I for x and j for y. Those are not the vectors I and j. Those are just my indices. They're going to count from 1 to the number of subintervals. And let's just say I chopped the x-axis into m pieces. So as I've drawn this here, m would be 1, 2, 3, 4, 5, 6. And I've chopped the y-axis into n pieces. As I've drawn it here, n is 1, 2, 3, 4. Okay. All right. And then I can refer to my subrectangles as this one would be the 1, 2, 3. This would be the 3, 2. It's in the third column, second row. Okay, excellent. Then I need to approximate. So I'm going to approximate the signed volume that lies above or below each one of these subrectangles. So let's just suppose that this is the ijth rectangle. There's my delta x and my delta y. Again, I don't need to chop it so that delta x is the same for every piece, but it's simpler if I do, so I'm going to. I'm using a regular partition for both the x-axis and the y-axis so that all of my subrectangles are the same size. Okay. Now, I might have a sort of blobular region here that looks something like this. If this is the surface of f of xy that lies above that rectangle, I don't have a nice geometric formula for that. And the problem is very similar to the problem that we encountered when we had functions of one variable. The problem is that that height is changing. So I'm going to employ exactly the same mathematical strategy of denial. I'm going to choose a representative point. Now I'm going to call that point Pij star. It's a point in the ijth subrectangle. The star probably actually isn't necessary here because I don't think I've called anything else Pij, but we're kind of used to having stars on our representative points, and I'm going to just be consistent with the notation of the book. They actually don't give it the nickname. They just go to Xij star, Yij star. I'm going to use the nickname Pij star just because it involves less writing. Okay. So there's going to be some height, some z value at that particular point. And so what I'm going to do is I'm going to approximate this volume with the volume of something that has a constant height equal to the value at Pij star. So I would have delta x, delta y, and then the height is just f evaluated at Pij star. So that the volume then would be f at Pij star times delta A, where delta A is the area of the base. So delta A, area of base, and of course I would calculate that as just delta x times delta y. Okay. So we're saying volume is area of the base times the height for a rectangle, and that's how we're going to approximate things. Okay. So then step 3, we add all of those up. So I'm going to have what's called a double Riemann sum. The sum as I goes from 1 to m of the sum as j goes from 1 to n of f of Pij star times delta A. That is a Riemann sum. It's a double Riemann sum. And here's how that works. When I is 1, that has me in this first column. Within this first column, I let j vary from 1 to n. So I would calculate the area of this rectangle, then this, then this, then this. So I've added up everything in that first column. Then I let I go to 2. Now I'm in this column. Within this column, I let j go from 1 to n. I calculate the signed volume of the rectangles lying above this column, and then I move to the next one, etc., etc. Okay, fabulous. And then, of course, this just gives me an approximation of the signed volume that I have. If I want to get to the actual right answer, I'm going to take a limit. So, step 4 is take a limit, and that's going to give us our definition for this double integral. The double integral over R of f of xy dA is going to be the limit as m and n both go to infinity of this double Riemann sum. The sum as I goes from 1 to m, sum as j goes from 1 to n, f of Pij star times delta A. And you can really see where the notation comes from. When I take the limit, my delta A becomes a dA. My function evaluated at a representative point becomes my function evaluated at an arbitrary point, and the limit of a double Riemann sum becomes a double integral. Pretty cool. Okay. Now, you will probably be relieved to know that we're not actually going to be evaluating any double integrals by taking the limit of a Riemann sum. So this is a little bit new, taking the limit as two variables both go to infinity. But we don't need to concern ourselves with that. We need to understand that they both have to go to infinity. Okay? But we're not going to actually evaluate anything this way because we know a lot about integration, so we can jump to some of the shortcuts, which is kind of nice. Okay? But in the homework, you might have a couple of problems where you're asked to approximate something using a Riemann sum, and conceptually this is incredibly important because we are going to see the same four-step process again and again and again as we work through this chapter and the next chapter as we look at applications of integrals and we try to figure out what integral would measure that. Our thought process is almost always going to be chop, approximate, add, take a limit. Okay,